Yo, what up guys? Hope you're all having a fantastic day. Today, I'm going to explain why I think segment trees are great, and I'm going to use Farron here as an example. So let's say one day, Farron wants to create a spell to get the total danger level of a group of chests, so she doesn't get eaten again. And now let's assume she already knows the danger level of each of the chests shown on the bottom row here. So this one would be 2, this one would be 6, and also that each chest has a fixed position. Given L and R, she wants to be able to find the total danger level within that range. So for example, if L was equal to 0 and R was equal to 2, then the total danger level within that range would be the sum of 2, 6, and 3, which would be 11. Now, we have a name for what she's trying to do here. It's what we call a range query. And you can range query for a lot of stuff. Like you can range query for max, total, min. And what's cool about range queries is that there are several ways to go about doing this. The first and most obvious way for her to do this is a linear scan. This means that if she wants to find the total danger level from L to R, then she'll need to sum up all the danger levels of these chests one by one. And this gives it an O of n complexity, where n is equal to the number of chests. And that's like alright, but what if she has to check the ranges, say n number of times? Then the complexity will grow to O of n squared, which is definitely too slow, and she's probably gonna spend an entire season checking the chest. If you guys notice, with multiple range checks, let's say this range over here, and then we'll add like one more over here, we're essentially recomputing the same thing multiple times. So is there a better way to avoid this and get faster results? There actually is, and it's what we call a prefix sum. Now, this is pretty neat. And what I'm gonna do is I'm gonna move all these values to a separate screen so we can kind of show how cool prefix sums are. Okay, boom. I moved everything to a separate screen so we can build out the prefix sum array. So what even is a prefix sum array? What it basically is an array where every point is the prefix sum of the original array. And an easy way to remember this is that it's essentially the sum of everything that got up to that point in the original array. So for example, if we want to find the prefix sum value of this point right here, then it would be the sum of this value 4 and everything before it. So it would be 4 plus 3, which is 7, plus 6, which is 13, plus 2, which is 15. So it would be 15 over here. And an easy way to build out this prefix sum is by doing what we call a running total. So we'll just total everything up. 2 plus 6 is 8, 8 plus 3 is 11, and so forth. Now the neat thing about a prefix sum is we can do range queries in 0.1 time, which is super fast. And we can use this neat formula where essentially if we want to find the range total of like 2 over here and 5 over here, which is 9 by the way, what we can do is we can look at the prefix sum array values and we can apply this following formula. Prefix R minus prefix L minus 1. And what is this? It's 25 minus 16, which is equal to 9. Okay, so this is easy, right? So why do I even bother talking about wanting a segment tree? If we can just do everything in 0.1 time, which is basically instant, what's the use of a segment tree? Which attempts to do the same thing, because it can't get faster than 0.1. Well, it's because prefix sums have this huge weakness. Let's say during like magic practice, Farron goes ahead and destroys one of the chests, and this makes the danger level of the chest in that area 0. Can you guys see what happens to the prefix sum? And now what we can see is these values are stale, right? They don't represent the current version of the data. So if the danger levels of the chest are frequently changing and we're doing O of n queries, we're back to O of n squared time. Why? Because we'll continually need to reset the prefix sum array by doing this whole like running total sequence. And now we're back to O of n squared. So this is why we need a segment tree. Okay, boom, they're nodes now. So the main idea behind segment trees is kind of like the thought of why don't we create imaginary nodes that represent the total of the values they're responsible for. So let me create an imaginary node for 2 and 6 over here. It would be 8, and this would be the range total of these two nodes. Now, if we just keep doing this for each node and fully build out a tree, then let's see what happens. Okay guys, can you kind of see where I'm heading at right now? The root node becomes the total sum of all of the nodes. So let's imagine all of the leaf nodes are the following ranges. Okay, boom. Now it kind of makes sense for the next level to be these ranges then, right? As they represent the sum of their children. So this would be 0 to 1 and so forth. Okay, boom. The tree is complete and the root node represents the total of all the nodes at the bottom. And now that's it. That's all a segment tree is. Just like its name, it's just a tree where every node represents a segment. It might be a total sum segment, it might be a max segment, it might be a min segment, but that's all there is to it. Now, okay, you're probably wondering, what if the range doesn't match the ranges inside of the tree? For example, what if we want the ranges 4 to 6? We can't return that exact value, right? Because it's not in the tree. The answer to that question is to just follow this one rule. We want to return every range that's inside of the range we're trying to find, and we want to ignore all the rest. So, for example, we want to ignore something like 2, 3, because there's no way this total will ever contribute to this range, right? However, we want to include 4, 5, because we know for a fact that this will contribute to the range sum of 4 to 6. And we also want to include 6, 6 over here, because we know that it'll contribute to the range sum of 4 to 6, because it's inside of it, right? And when we sum these two together, we get 8. Now let's manually calculate what the range 4 to 6 is. It's 1 plus 5 plus 2, which is 8, right? Now this is how range queries are done in segment trees. And let's write down exactly this kind of thought process we just laid out. Now this part is actually pretty important, and it's going to be our base case for our range query method. So there are going to be two methods that we're going to place in our segment tree. The first is our point update method. Second is our range query method. So this is the second one. Let's let L and R be the actual range. So it would be something like 4, 7 here. And let's let X and Y be the range we're querying. If the range we're currently looking at is outside the range we're querying, so that would mean X is greater than R or L is greater than Y, then we want to ignore it. Or in this case, we want to return like a sentinel value. So something like return 0. So it doesn't add to the range sum. Now, if it's inside the range, so X is less than equal to L and R is less than equal to Y, then what we want to do, okay, this is getting in the way, my bad, is return its value. So return val. And this ensures it contributes to the overall range we're trying to find. Now, there's one more case, and that's if the current range we're looking at is the one covering the range we're querying. So what we want to do here is we say, yeah, we can't let this entire range contribute to our range query. So we want to find ranges that are more specific by visiting the node's children. An example of this would be 0, 7, right? It covers the range we're querying, which would be 4 to 6. So we want to get more granular and specific. And what we want to do is we want to send this range query function to its children and apply this rule over here to them. So that's everything for the range query method. Now let's move on to the most important part of the segment tree. All right, let's see how we can find our way to the single node from the root node. Okay, let's say we want to find old 2 right here, node 6. We start at the root node, and what do we know now? Okay, so we're presented with two choices, right? We either can go left or we can either go right. And remember, we can't just simply modify a non-leaf node because they wouldn't represent a single node. They represent a range, right? The single nodes are all down at the leaf. Now, this isn't a very hard choice, actually. We just go with the choice that contains our node position. So, for example, we have the choices of the ranges 0 to 3 and 4 to 7. Why would we go down this range when it doesn't contain node 6 at all? It's just 0 to 3. What we want to do is we want to go down this path instead. So we're going to end up over here, right? Now we're left with two decisions again. Do we want to go down this path to the right or to the left? Now we apply the same logic and we say, okay, we don't want to go down this path because it won't contain the node 6 at all. So we go down this path. And now we're just left with two choices. 6 or 7. 6, 7. Oh God. Sorry, I'm back. And we can obviously just choose 6 over here. And this is kind of the logic we're gonna use to update the leaf nodes, which represent the actual node values. Okay, let's write that decision making down. So first, we're gonna let m equal to L plus R minus L divided by 2. And remember again, L and R represent the actual range value. So L would be 0 here and R would be 3 here. And the reason why we're not just doing L plus R divided by 2 to find the middle value is because we don't want to deal with integer overflow, which sucks. Now, if the single node position we're trying to go for is greater than m, so let's let that be index. If it's greater than m, then what we want to do is we want to go right. And conversely, if the index is less than or equal to m, then we want to go left. And this is just exactly what we did. Okay, quickly, when do we know when to stop? Well, it's pretty simple. We know it's a single node if, like I said, L is equal to R. So if L is equal to R, that's our base case. We just want to modify and then we want to return. Now, this is probably the most important part of getting this segment tree to work correctly. Guys, as you can imagine, when we change the value down here, let's say to like 3, then we'll need to update the nodes that have our updated node in its range. Or not, the values are going to be stale and inaccurate. So we're going to need to go ahead and just do that. Let's change this to 9, change this to 21, and change this to 31. As we go back up, we always need to remember to update our nodes with the values of the updated children. And if we place this after we place our functions to move downwards, then this will naturally happen via recursion. And that's it. Now, just how fast is all of this, since we've basically covered everything? Well, we know that each step down the tree, right, halves the range we're looking at, since we split it at the midpoint. So halving repeatedly means the number of levels is log n. And what we're doing with both the range and update method is just walking down the height of the tree. Therefore, both operations are log n. So now with the segment tree, Fairbairn can properly check the total danger level of a group of chess And isn't that great? Now, all of this gives us a launching pad to code everything up super quickly. So I beg you, just stay until the end of the video and you'll be able to code up the segment trees and like flex on all your friends when your lead code solutions are like way faster than theirs. So I promise it's going to be simple, and let's get straight to it. Okay guys, so let's review the code real quick. So this will be the complete segment tree implementation. Let's start from the very start first. We're gonna need a way to store all the values. So of course we're gonna initialize a vector int called values, and we're also gonna need an integer to represent the size of the values. And the really interesting thing here is that the actual size of the segment tree is usually always bounded by 4 times its actual size, because it's never gonna be like the actual size of the nodes, right? Because it's gonna contain the range sum of the nodes as well, like these imaginary nodes that I talked about. And a key thing to note here as well is that we're representing the tree in a similar way we do with heaps, where the left and right child are I, the position of the node, multiplied by 2 plus 1 or plus 2. So we're just basically doing that over here. And yeah, let's move on to the first method. That would be the update method. And as we know, the base case is if L is equal to R, then that's not really a range, that's just a single node. So we just change the value and we return. I over here represents the actual index in the segment tree, while index is kind of like the index of the node we're trying to get into, imagining the segment tree as size n, basically the original like values we're working with. Then what we're gonna do is we're gonna take the integer m, the middle point, and we're gonna run the same procedure where essentially if the index we're looking for is less than or equal to the middle point, then we're gonna recurse to the left. Otherwise, we're gonna recurse to the right. And remember, as we recurse up, we wanna update the values since they'll change. Okay, moving on to the range query. We're just gonna repeat the base case. Essentially, if it's outside the range, then we're gonna return a sentinel value, or basically a value that won't affect the final result, basically like a dud. That would be 0 in this case. And if it's completely within, then we just want to go ahead and return whatever value it's storing. And over here, this is like the third case that I talked about. If it's within, if the query range is within the actual range, like completely within it, then we want to just go to the children and essentially find more specific ranges. And yeah, that's pretty much it. Hope you guys enjoyed. Peace.